Hi everyone, my name's Tim, and this is the Solid State Workshop. Today's video is entitled, An Introduction to Simple Electric Circuits. And if you've been following my channel, you'd know that I actually uploaded a video with the same exact title about a year ago. So this might be kind of weird because, well, why am I uploading this again? I already did it. Well, after watching that video, I realized, I could have said some things a little bit better. And I could have explained a couple concepts a little more clearly. And, there's just a couple things I wasn't too happy about with that video. So I'm going to try to fix those mistakes, be a little more clear in this video, and hopefully paint a nice picture as to what simple electric circuits are. Let's go. So to start off, we're going to use an analogy, because sometimes hopping right into the whole electric stuff it's not always the best way to go. So what we're going to use is this thing called the hydraulic circuit. And a hydraulic circuit means to do with water. Hydro, to do with water. So we're going to imagine that this blue circle thing here, that's a pipe. And inside that pipe we have volumes of water. So we're going to say that each one of these little spheres of these white spheres here, we're going to say that those are volumes of water. Say a liter apiece. Alright? So we have, I don't know what, 20 liters in this pipe or something. And we're going to say that this pipe is completely filled with water. So there's no air in this pipe at all, just completely filled with water. Fair enough? Okay, now we have two more elements in this hydraulic circuit. We have a pump, and we have a valve. And we're going to see exactly kind of how they're defined and what they do later, but I'm sure you kind of are familiar with these two things. So let's see what would happen, say, if we turned on our pump and we kept our valve completely open. What's going to happen if we turn on a pump right now? Well, the water is going to move through that circuit really, really fast, and it's going to be all happy and all honky-dory, right? Great. Now, let's say we closed our valve, so now it's only 50% open, right? What's going to happen? Well, our water is going to move through that pipe half as quickly because our valve is halfway open. And the pump is pushing, but that opening is only half as big, so the water has to move more slowly. And let's say we put it on 25%, well, you get the point. The water moves even more slowly. Even though that pump is still pushing just as hard, it's going to move even more slowly because that valve is more closed. So just, of course, keep this in your head, and hopefully this will make sense a little later. If it doesn't already. So let's do a quick overview of the different elements of our hydraulic circuit. First one we'll look at is the piping. And piping is what contains the water. Wherever the piping goes, the water flows. And in our example, the size of the pipe, it doesn't matter. Don't worry about the pipe. If it's big or small, whatever, doesn't matter. The next thing we're going to look at is water. And water is the substance that is flowing through the circuit. That's fairly obvious. But one thing that we should keep in mind, and that will make sense when we go on to electricity, is that the volume of this water remains constant. Regardless of how quickly we pump the water or how much the valve is closed, the volume of that water is always the same. Cool. The next thing we'll look at is the pump. And the pump gives water kinetic energy. It accelerates it through the piping. It puts the water in motion. A more powerful pump can move more water more quickly. And our last circuit element is the valve. And a valve regulates the rate of flow of water in a circuit. So if we turn a valve completely open, the maximum rate of flow is achieved. But if the valve is completely closed, well, then there's no flow. However, we can adjust the valve to be slightly open or slightly closed or anywhere in between. And that is what can regulate how much water flows and how quickly. So how do you actually define rate of flow, or flow rate? Well, let's zoom in on our circuit here, our hydraulic circuit. and we're going to put this point K here, and we can say that flow rate is defined as the volume that passes through this point K. So the volume of water that passes through that point K in a certain amount of time. And that'll give you the definition of flow rate. So just to remind ourselves, one of those little white spheres there is equal to 1 liter of water, which is also equal to 3.3 times 10 to the 25th molecules of water. And we'll see why that's important later, but for now it's 1 liter. And so let's just say we put this in motion. We turned on the pump and we let the water flow in our circuit. So how do we find flow rate? Well, we just count how many liters of water pass that point K in a certain amount of time, and simple arithmetic will tell us the flow rate. So let's go. 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. And so I counted 5 liters of water passing through that point K, and it took it 5 seconds for that to happen. So if we divide 5 liters over 5 seconds, we'll get 5 liters per second, and that's our flow rate. So that's pretty easy to understand. Cool. So now we're going to move on to electric stuff and all that fun stuff. So bear with me. So we should talk about the idea of electric charge. And well, what exactly is electric charge? Well, electric charge is an intrinsic property of all matter that causes a force to be exerted when some electrically charged matter is near other electrically charged matter. So we know that like charges, like 2 protons, they repel each other like that. And that opposite charges, like a proton and an electron, they are attracted to each other when they're near each other. So we'll see why this matters in a couple of slides, but this is something that you should understand when you're talking about moving these charges around and why they want to move around. The unit of charge is the coulomb, which we use a capital C for. Now, if we want to talk about charges without a unit, we can use little q instead. But so in an equation, you might see something like Q over V, and the Q means charge, and if you were to actually plug in a value there, you would use a value that was measured in coulombs. So an electron has a very, very, very small charge. In fact, if you wanted to make a whole coulomb's worth of charge, you would need 6.2 times 10 to the 18th electrons. So that's a whole lot of electrons to make this 1 coulomb of charge. And if that doesn't make sense, you can think about a coulomb's worth of electrons as something like a liter's worth of water molecules. So in a slide or two ago, we talked about a liter of water being 3.3 times 10 to the 25th molecules of water. So this is like the same idea. In 1 liter, there's a certain amount of water molecules, and in 1 coulomb, there's a certain amount of electrons that make up that 1 coulomb. So yeah, thanks for sticking with me. We're going to finally start talking about electric circuits and all the fun that entails. I know this has probably been the worst video I've ever seen in your life, so I have no idea why you're still watching it, but thank you. And we're going to start talking about the electric circuit. So on the right is our representation of an electric circuit. As you can see, it looks kind of similar to our whole hydraulic circuit business here on the left, and we're going to see that that's kind of true. There's a lot of similarities between our hydraulic circuit and our electric circuit. So let's figure out what those are. Thinking back to our hydraulic circuit, we had piping and water. And piping was what contained the water, and the water was what we were moving around in our hydraulic circuit. And in a similar fashion, in an electric circuit, we have copper wire, and within our copper wire we have these free charges, these free electrons. And why is there free electrons in a copper wire? Well, copper atoms natively just have these electrons that are not bound to any one copper atom. They can kind of bounce around between different atoms in that wire and do what they please. They kind of move in random motion, these electrons. So these electrons are already present in the wire. We don't need to add these electrons to the wire. And it's these free electrons that are kind of not anchored down that we can move around using something like a battery. Now, before we start talking about batteries, let's talk about pumps. And what do pumps do? Well, pumps put water in motion. They move water and push on the water and get it around the pipe. And in a very similar way, a battery pushes on the electrons in a copper wire and in a circuit and moves them around a circuit. And well, how can a battery do that? Let's look internally, quickly, into how a battery works. So, internally inside a battery, there are two reactions happening. One at the negative terminal and one at the positive terminal. And at the negative terminal, there's a chemical reaction happening that wants to give off electrons. That's what it wants to do. It wants to give off these electrons. And at the positive terminal, there's an electron that is more eager to accept electrons. Or in other words, at the positive terminal, there's a reaction happening that's less likely to give up its electrons. So there is a difference here. On the top, on the negative terminal, it's really, really eager to get rid of electrons. And on the positive terminal, it's not quite as eager. So there's a difference in eagerness here. And this difference in eagerness is what causes electrons to want to flow from negative to positive here. And well, what does that mean and why? Well, nature kind of works by moving to the more favorable condition, the condition at which there's a lower energy level. So to kind of equalize, to become at equilibrium, this negative terminal wants to get rid of its electrons, and the positive terminal wants to accept those electrons. And that's what happens. And that's how electrons move from the negative terminal to the positive terminal through an external circuit and make magic happen. So let's think about one more thing before we move on, and that's the whole concept of pushing on the electrons here. And well, what do I mean by that? So when the negative terminal gets rid of an electron, it introduces one more electron into this wire here than that was there previously. And so there's one more electron in that wire, but there's not exactly space for one more electron in that wire, if you want to think about it that way. So what happens? That one electron pushes on all of the other electrons in that wire, and it pushes on every single one of them until one at the very end, at the positive terminal, pops out into the positive terminal, because there's not really space for that electron in the copper wire. And so if you want to think about it another way, think about it as a straw completely filled with marbles. If we try to add one more marble to that straw, well, what happens? You put one marble in on one end, and on the other end, out pops a marble, because there wasn't room for that marble. So that's kind of how this is working. When you introduce that one electron onto the copper wire from the negative end here, because like charges repel each other, as we learned in the previous slide, we know like charges repel each other, they all repel each other until one electron comes out on the positive end over here. And so even though the electron produced at the negative terminal is still probably very close to the negative terminal, it managed to cause all of the electrons in that wire to move, or at least just a smidgen, but they all moved. So although that electron didn't necessarily go racing automatically to the positive terminal, it caused a movement of electrons in the wire. Hopefully that made sense. On the last slide, we talked about a difference in eagerness between the negative and positive terminals of a battery. At the negative terminal, we had a high eagerness for electrons to leave. And at the positive terminal, there was a much lower eagerness for electrons to leave. And it's this difference in eagerness that drove electrons from one terminal to the other through a circuit. Now, there's a technical name for this difference in eagerness, and you probably guessed it since it's on your screen. It's potential difference, meaning the difference in electric potential between 2 points. So in this case, between the negative and positive terminals of the battery. So at the negative terminal, electrons are at a high potential. And at the positive terminal down here, well, they're at the end of their journey, they're at a lower potential. The unit of potential difference is the volt. And you've probably heard of the term voltage. And we have 1.5 volt batteries and 9 volt batteries and 120 volts or 240 volts at our wall outlets. And what do all these numbers mean? Well, basically, the higher the voltage, so if we increase the voltage, the charge or the electrons will move faster through our given circuit, meaning there's more energy transferred to the electrons in the circuit, and it moves them around more quickly if we were to up the voltage. Now, by definition, a volt is the amount of energy per unit charge, or 1 volt is defined as 1 joule, the unit of energy, over 1 coulomb, which is the unit of charge. So that is the energy per unit charge. Before we were talking about valves and how they limit the rate of flow of water in a hydraulic circuit. So basically they dictate how much water passes a certain point in a certain amount of time. And in a very similar way, a resistor limits the rate of flow of charge in an electric circuit. So if you have a greater resistance, use a resistor with a greater value, then you decrease the rate of flow. And if you use a resistance that's relatively low, then you allow a greater rate of flow of charge. We use the unit ohm to measure resistance, and ohm is named after Mr. George Ohm, who was a physicist a couple hundred years ago. And we use the symbol omega. Very appropriate, right? Cool. Typical resistors that we use in circuits and circuit boards might look something like this. And these are pretty small devices. They're usually around 5 to 10 millimeters, or between 1/4 and 3/4 of an inch, or something around there. They're pretty small. And these are our typical resistors. This is what most people think about when they hear the word resistor. The blue one on top might be a metal film type resistor. The tan one on the bottom is probably a carbon film type resistor. And the one in the middle might be some sort of, fireproof metal oxide resistor or something like that. But this is what we typically think about when we talk about resistors. However, there are other types of quote-unquote resistors out there, and they come in different forms. For example, a commonly used resistor is a light bulb. A light bulb is basically resistance. It heats up a lot, but it also creates light, and that's the useful part of a light bulb. And of course, we also have space heaters and all sorts of electric heaters. And in the same fashion, toasters and anything that has a heating element that you plug into the wall is basically a resistance. So you can think of those as resistors. Getting back on track, we've been talking a lot about moving charge from one point to another, from the negative terminal of a battery to the positive terminal of a battery. That movement or flow of charge is what is known as electric current. An electric current is how much charge passes a certain point in a certain amount of time. Or if you'd like to express that at a particular instant, you can write dq over dt. And the unit of electric current is the ampere, and we use a capital A for ampere. And you have 1 ampere of current when you have 1 coulomb passing a certain point in the circuit in a matter of 1 second. And that's how you have 1 ampere. Cool. If you think back to our hydraulic circuit analogy, we talked about flow rate. And this slide looks a lot like the slide for flow rate, except now we're talking about electric current. And the two are very much related. Flow rate and electric current are very, very similar. And so we can set up a point K like we had in our flow rate example. And we know that current, electric current, equals the amount of charge that passes through K in a certain amount of time. And we know that one of these bronze/brown spheres here is 1 coulomb of charge, or 6.2 times 10 to the 18th electrons. So once again, we can count how many electrons or how much charge passes through that point K in a certain amount of time, and that'll tell us what our current is. So let's figure that out. 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. And okay, in 5 seconds, if you counted with me, you would see that 5 coulombs of charge passed K in 5 seconds. So you do the math, 5 over 5, and that's 1 ampere. So that's our current. Makes sense. If you're going to take anything from this video, what should it be, right? So let's put everything together here and try to make sense of it all. So we've learned that when you connect a resistor, or more simply just a wire, across 2 terminals of a battery, that charge will flow from the negative terminal through the wire into the resistor, back through another wire, and back into the battery. And that's because the battery drives those charges through the circuit. We've learned that a battery with a higher voltage will cause the charge to move more quickly through the circuit, and that will cause a greater current, because current is how much charge passes in a certain amount of time. We've also learned that a resistor is a device that limits the rate at which the charge flows, so it limits current. And if we choose a resistor with a greater resistance, then the charge flows more slowly, and we have a smaller current. And the opposite way around, if we choose a resistor with a low resistance, the charge moves more quickly, or we have a greater current. So we have a couple things that we're working with here. We're working with the voltage of the battery, the value of the resistor, the resistance of the resistor, and we're working with how quickly the charge flows through the circuit, or the current. So that's 3 things: battery voltage, resistance, and current. So 3 things. So there must be some sort of relationship between them, and there is, and it's called Ohm's law. Ohm's law is a pretty simple relationship. It just relates 3 things: voltage, resistance, and current. And we can write it as current equals potential difference, or voltage, over resistance. Or more shortly, we can write it as I for current equals V over R. And we use I to represent current, and we can't use C, because C, as we know, is the symbol used for the coulomb for charge. So instead of writing C, we write I for current. That's just some thing that people said a long time ago. You might also see V as written as E, capital E. And the reason that you might see an E instead of a V, or vice versa, is because voltage used to be called electromotive force, but that's of days past, and it's not a force, so don't worry about that. But if you do see I equals E over R, that's the same thing as I equals V over R. And now, of course, we can arrange or rearrange this formula to solve for any unknown element in this equation. So if we don't know current, we can set it up in this fashion. And if we don't know voltage, we can rearrange to solve for voltage or resistance. but of course we have to know 2 of those elements there. So let's do an example. For example, if we have a 10-volt battery and we hook up a 100 ohm resistor to it, we put one leg of the resistor on the positive end and one leg of the resistor on the negative end, we can determine the current in the circuit. So how are we going to do this? Well, very simply, we know I equals V over R, and we know V is 10 volts, and we know resistance, or R, is 100 ohms, so you very simply divide 10 by 100, and you will get 0.1 ampere. Easy as pie. So let's say that we were to halve the resistance, and instead of using a 100 ohm resistor, we use a 50 ohm resistor, so half the resistance. And we once again plug it in, 10 over 50, and we get 0.2 amperes, so double the current. So by halving the resistance, we have doubled the current. And I hope that makes sense. It's a simple relationship. So you might run into a case where you need to determine an unknown resistance, and you have the source voltage of your battery, and you have the current in the circuit, but you don't know what the value of that one resistor is. So if we know the current and we know the voltage, we can totally determine the value of that resistor. Say the battery measured 5 volts across the terminals, and we had a current of 0.25 amps. We can simply rearrange Ohm's law as R equals V over I, and divide 5 by 0.25, and we would figure out that that resistor is a 20 ohm resistor. And it's as simple as that. A couple quick notes about measurements. If you're in the lab and you want to take measurements for yourself, well, how are you going to do it? So if you want to measure voltage, what you simply do is probe across 2 points in a circuit. And why do you probe across 2 points? Because we know that voltage is a difference. So what you do is you get yourself one of these multimeters here, which is this yellow thing, and you plug 2 probes in, one into the volts jack and one into the comm jack. Set your function to volts, usually volts DC in this case, using the switch here, the selector switch, and you probe across a device, or across 2 points in a circuit. So here we're probing at the positive terminal and at the negative terminal of a battery, and the multimeter tells us that the battery is providing 1.5 volts between its terminals. So that's how you do that. Now say we wanted to measure current. Well, that's a little more tricky, but not too hard. Now remember, current is the flow of charge through a circuit, so to see how much charge is flowing past a certain point, we have to put the meter in series with the load, meaning in series with the resistor, meaning directly in line with the resistor, so that all the charge that flows through the resistor also flows through the meter. And so this is how we set it up. We break the circuit at one point. So traditionally we'd have a wire connected from here down to the resistor, and then the resistor would go back to the battery. But now instead we're going to put the meter in line with that resistor and make sure that we set the meter to the amps range, and we switch from the volts jack to the amps jack, and we still use the comm jack, and we put the meter in line with our resistor, and this will tell us how much current there is in the circuit. And it's very simple. So say here we have a 3 ohm resistor, and we'll just assume that this is a 1.5 volt battery, then we would have a current of 0.5 amps, and that's what you see here. Thank you so much for watching. Hopefully you've learned something from this video. Hopefully you enjoyed this video. I know I enjoyed making this video for the second time around. I taught myself a thing or two and cleaned up my act a little bit, I think. So I'd love to hear your feedback. If you liked this video, please thumbs it up. If you didn't like this video, go ahead and break my heart with a thumbs down. But if you want more more videos of this type, you can subscribe to my channel and you'll see the updates. And anything else, just shoot it my way. If you have any video ideas, I can give them a shot. I'm not a genius, so no guarantees, but I'm really open to anything. So thanks a lot and have a lovely day.